Today's automobile is a reliable vehicle, so reliable that we take it for granted. With so many cars in use, so many miles traveled, and so little trouble, we're prone to ignore possible failure. We're so sure the car will start every time that we wait until the last minute to leave for the office. We're so sure of its response that we pass with little room to spare. We're so sure the brakes will work that we crowd the car ahead. But sometimes there are failures. For instance, the brake pedal may go to the floor without warning. Of course, there's the emergency brake, but this can lead to additional hazards. Concern over what happens when brakes fail has resulted in considerable study and research. The purpose of this film is to present some of the results of one of these studies. At the landing loads track, one of the facilities of the Langley Research Center, studies have been made on the behavior of aircraft tires on wet runways. In the course of this study, it was learned that under speeds and water depths frequently encountered, pneumatic tires will be lifted clear of the pavement and hydroplane, an effect similar to water skiing. This, of course, results in the loss of braking and steering control. The phenomenon occurs with automobile tires as well as with aircraft tires. Since the technology developed by NASA was directly applicable to automobiles, the NASA supported the Bureau of Public Roads of the Department of Commerce in demonstrations of the behavior of automobiles on wet roads for the purpose of informing the driving public of this little-known hydroplaning hazard. As a part of this program, automobile behavior resulting from brake system failure was demonstrated by locking the rear wheels with the emergency brake. In response, the car spins through 180 degrees with little chance of recovery. The dangerous vehicle reaction to rear wheel braking, reinforced by the GSA dual braking specification for government vehicles, led to a limited investigation of various braking combinations in use today. A simple hydraulic brake system has one master cylinder to supply pressure to all four wheels. In the event of a component failure, fluid pressure drops throughout the system. To prevent total loss of braking ability, one solution is to make the entire system redundant. That is, two master cylinders, two cylinders at each wheel, and two separate brake lines, each system being independent of the other. Another solution is to provide two master cylinders, but with each supplying only two wheels. With this method, however, it must be determined which two wheels will be braked by each of the two master cylinders. In order to explore the advantages and disadvantages of various braking arrangements, a conventional American automobile provided by the GSA was modified and a test program scheduled. A brake pressure manifold was installed with a shut-off valve for each wheel so that any combination of wheel braking could be pre-selected. Red lights were installed on top of the car and on the dashboard to indicate when brakes were applied. The tests were conducted at the NASA Wallops Station, Wallops Island, Virginia. At the test site, 3 representative braking surfaces were used. Dry concrete to provide an excellent traction surface, concrete covered with water averaging about 1/10 of an inch in depth for moderate traction, and a specially prepared area covered with a black highway sealing material, which, when wet, provided a slippery but still realistic braking surface. A variety of speeds and tire tread configurations were investigated on these surfaces, and all braking was done with locked wheels, both to provide a common base for comparison and to simulate a highway panic situation. The difference in vehicle response to various wheel brake combinations will be illustrated on the wet black test surface at 30 miles per hour and with good tires. For the first test, the normal four-wheel braking arrangement was used. With straight line braking, the car displays neutral stability and tends to continue in the same direction following brake application. When braking on a 500-foot radius curve, the car tends to be neutrally stable, but there is a complete loss of directional control, since a tire must be rotating to develop any steering forces. With the wheels locked, the tire becomes a sliding body and no longer can be used to stabilize or to steer the car. For the next test, only the front brakes were applied, simulating a partial system failure of a dual system having the two front and two rear wheels connected to separate master cylinders. The technician closes the valves to the rear wheel brakes, permitting application of fluid pressure only to the front wheels when brakes are applied. Traveling in a straight line with the front wheels locked, the car is inherently stable since the two rear wheels are rotating. On the curved course, the car is stable, but again with the front wheels locked, no cornering force can be developed for steering. For the next test, only the rear wheel brakes were applied. The valves are adjusted such that brake application will simulate the use of the emergency brake, which would be used in the event of a failure in a single system car or failure of the front wheel brakes in a dual system. On the straight course, the brakes are applied, locking the rear wheels. In this condition, the car shows total instability, since the locked rear wheels provide no stabilizing forces and corrective action by the driver has little effect. Corrective action is even less effective on the curved course, since the car spins out of control more quickly in the turn. When brakes are applied, as indicated by the red light on the dash, spin out follows almost immediately. Stability can be recovered only by releasing the brakes. Since braking front wheels only caused loss of steering, and braking rear wheels only caused instability, a system of braking one front and one rear wheel was investigated. In the first case, system failure was simulated by applying only the left front and right rear brakes. With this condition, stability is provided by the one rotating rear wheel. To compare the opposite diagonal arrangement, the valves are adjusted for right front, left rear braking. With the opposite diagonal pair on the curved course, the car again shows stability and also demonstrates controllability, since one front wheel is rotating. Thus, it seems there is a definite advantage with the diagonal system. Upon completion of the study of the effects on stability and controllability, the test course was prepared for studies on the effects of the various braking arrangements on stopping distance. Wet concrete was used in these tests since the differences in stopping distance are more apparent. With four wheels locked, the test car required 60 feet to stop. With only the front wheels locked, 96 feet. With diagonal wheels locked, 110 feet. With only the rear wheels locked, 153 feet. Thus, the diagonal system offers stopping distances which are comparable to other systems, while providing improved margins of stability and controllability. Another factor considered was the severity of sudden steering forces caused by unanticipated diagonal braking. After briefing by test personnel, a group of volunteers were asked to drive the test car, but were not told that the brakes would be applied diagonally. The left front, right rear combination was chosen, and the tests were run on dry concrete to provide the highest steering forces. Each driver was instructed to apply brakes at the first set of traffic cones and attempt to stop before overrunning the second set. At 20 miles per hour, a definite force was experienced on the wheel, but regardless of the element of surprise, the driver was able to maintain control. From a different viewpoint, it can be seen that the car did not cross the center line. At 40 miles per hour, the driver applies a double course correction and is able to keep the car within the limits of the test lane. In summary, although today's automobile brake system is highly reliable, the danger inherent in possible brake failure demands a backup system. The backup might be a dual four-wheel system or a simpler two-wheel pairing. In comparing various two-wheel arrangements, the results of this study indicate that a diagonally connected brake system offers definite advantages in stability and directional control and offers reasonable stopping distances in the event of partial system failure. Further, the results show that despite the unexpected steering wheel forces of diagonal braking, the driver is able to control the vehicle within safe limits. These tests have pointed the way towards safer braking systems, which by maintaining stability and steering control could mean the difference between safety and tragedy. We are so sure of its response that we pass with little room to spare. We are so sure the brakes will work that we crowd the car ahead. But sometimes there are failures. For instance, the brake pedal may go to the floor without warning. Of course, there's the emergency brake, but this can lead to additional hazards. A minute to leave for the office. Today's automobile is a reliable vehicle, so reliable that we take it for granted. With so many cars in use, so many miles traveled, and so little trouble, we are prone to ignore possible failure. We are so sure the car will start every time that we wait until the last